So, today is a continuation, of course. So, discussion of the drum. Complex. But I will, of course, review as I usually try to do. So let's have a somewhat detailed review of where we are. If we have M is, and I will fix this as an n-dimensional smooth manifold. And of course, we immediately then associate to this the tangent bundle and the cotangent bundle. The fundamental vector bundles. Just recalling that the sections of the tangent bundle, as we're calling, this is the same thing in a vector field. And the sections of the cotangent bundle are one-forms. And I joked around yesterday about how important the full tensor bundle is. Let's even give it a name. In the lecture notes, I will call it the tensor bundle of the manifold. Just some incredibly big bundle. So the full tensor product of the tangent bundle, the full tensor product of the cotangent bundle. That's a huge infinite dimensional bundle, obviously, because of all these tensors, it's very infinite dimensional. So usually when we're interested in handling something like this, what we usually look at is the k-fold tensor product of the tangent bundle, tensor the L-fold. So just some subbundle, which is now finite dimensional fiber. And here, for example, a frame in that bundle in this bundle, so let me write it again, it doesn't hurt. And this bundle is finite dimensional vector bundle. These are tensors, and they, by the way, in physics, they will talk about tensors of a certain covariant type and a certain contravariant type. This would be covariant, this would be contravariant. So probably they would say tensors of type LK. So a frame here would be of the form, let me write it if you don't mind, dxi tensor dxj. So to avoid all sorts of indices problems. So I is a multi-index of length k, and j is a multi-index of length l. And then, of course, it's clear what this means. But let me just write out, for example. So I mean by dxi, you will see this in the literature. dxi1 tensor dx. Ik. And similarly for dxj, dxj1, dxjl. Those are frames, that's the local frame change of frame is the expected way. So in these complicated tensor bundles, it's very complicated. So I'd be the first to say that these are very complicated. Now, because of physics and other reasons, there are very important associated bundles. I will mention two. Well, it doesn't matter which side, but the main one is that I want to talk about today is the Grassmann bundle. Which I mean by this the full exterior product of the cotension bundle. This is important. Others, for example, the k-fold symmetric product of the tangent bundle, okay, all possible powers of k, etc. These are bundles, and it's clear what you do. You understand what these things mean at the vector space level, and you just integrate that into a bundle, and that's your bundle. That's the definition. So, and now we come to our study of the exterior algebra. Of the manifold. And this is with respect to this exterior algebra bundle. And we then look at the bundles. The various bundles, starting with the cotangent bundle, or maybe the trivial bundle, but let's start with the cotangent bundle. The first exterior product. Okay, this is okay. I will get it right in a minute. And the k-fold exterior product, the cotangent bundle. This is somehow the first exterior product, then the second, and the third, and so on. And finally, the nth exterior product. So this is the first, and somehow the zeroth is missing here. It's somehow just the field itself. Okay, so let's recall then what we're dealing with here. We're dealing with a frame again. So here we use tensors. So the frame for, say, the k-cotangent bundle is then dxi1 with dxik. And here, of course, we arrange these things in increasing order. We talked about this yesterday. For k someplace between 1 and in the middle, this is going to be huge. At the end, it's just one-dimensional. Okay. Of course, to be precise, I would have some choice of coordinates here. And change of coordinates is by the action of GLNR, and you have to say what the action is on the frame. So change of basis, I won't write alpha, it's very tiring. It's just the usual diagonal action of this group. Diagonal or abstract. This is how frames change in this very complicated bundle. So this is what I'm going to do. I'm going to devote my attention to this today. I'm still reviewing, coming to the last part of my lecture last time. By definition, sections of the k-fold exterior power of the cotangent bundle, and these we know are things at least locally, are functions times these frame elements. These things deserve a name, and we abbreviate them like this. And something here, maybe I usually write Greek letters, is called, and let me emphasize, a differential K-form. So you should have the feeling that at a point, this fiber here is some terrible thing. It's just the exterior power of the cotangent space at that point. And a section of that bundle then associates, at least over this point at least, a section here. This will be a section, so alpha is a section. Alpha, it associates to this point a multilinear form, right? Because that's what the fiber is. It's a multilinear form, right? An alternating multilinear form. Okay, and a vector bundle is just you extend this all over the place, all these fibers, and they're put together in local frames and so on. And at every point is downstairs gets some form, and it varies smoothly. That's a section. So at each point is a multilinear form on a tangent space, and it varies smoothly. And the smooth change of variables is given by some type of very complicated higher order Jacobian, because this matrix A here, in some sense I should have written A is equal to G alpha beta, change of variables, and so it's acting diagonally in a very big space, so it's some complicated Jacobian type of transformation. These are differential K forms. It couldn't be simple. You just have the dual space of the tangent space, and all higher order forms, put this in a bundle, and these are sections. That's it, basta. Now, you were asking last time good questions related, and I can't remember the question, but I remember the answer a little bit, is what are these forms? What good are these forms? That's more or less your question. And what I said last time, I will say again, that the idea, the application of alpha, of such forms, or evaluation of alpha, is integrating alpha over k-dimensional submanifolds. I will speak at least a bit about how to do this integration, but let's just talk about it intuitively now, okay? So I don't want to go into the details now. But let's talk about M, an example, M, the manifold is some simple manifold, so M is equal to R3. Okay? So we don't have so much here. I mean, we just have functions, 1 forms, 2 forms, and 3 forms. And in R3, well, we have, here's the origin, and we have some coordinate axes and so on. And we have spheres here. So here's an example of a submanifold. N, say, is the unit sphere. Well, let's call it S2. So I claim with my K here that you integrate K forms over K-dimensional manifolds. That's what I'm saying. You integrate K forms over K-dimensional manifolds. And what's the point here? So everybody knows. Let's remember an analogy. Before we do this, let's remember an analogy of if I were a good teacher, I would have first started with 1 forms. Right? Well, I wanted to make something interesting, so I start with 2 forms. But let's start with 1 form. So you integrate over a curve, and it's completely clear, intuition-wise, physics-wise or anything, you measure and somehow the lengths, you add up the lengths of these infinitesimals. So what that means is you integrate the form over the curve is just what it means is, the curve says parameterized from 0 to 1. It means you integrate the pullback, say this curve is called gamma, you integrate the pullback of the form to the interval 0, 1, and what that does is it adds up the lengths of these things with the weight alpha. I mean, alpha is varying along there. We discussed this like a force field or something like that. Alpha is varying, so it's like integrating a function over the curve. You never integrate a function over a curve. You do one form over the curve. Even here, this is some function f of t dt, right? And this is the variation of the one form over the curve. So everybody understands that from elementary calculus, but then in physics people understand it in dimension 2 also, because here you have a point here, and then you have a frame in the tangent space here. So, yeah, E1, I don't care, E1, E2. And here we added up lengths here with weights, and here you add up areas with weights. You add up areas with weights. And adding up areas with weights is an integral over the sphere, right? And then what is an area? An area is the evaluation of a two-form on two vectors, because as you know, the evaluation of a two-form on two vectors is a determinant. And the determinant is the area. I'm sure you know this. The area, if you have a matrix, right, A, B, C, D, those are two vectors, and they span a parallelogram, and the determinant is the area. In general, if you have k vectors, they span a k-dimensional object, and you evaluate a k-form on that, and you get a number, and that's the area weighted with that k-form, just as here these tangent vectors are weighted with whatever alpha is. In the long run, it's some function. Okay? By the way, it's weighted with orientation, because on a curve, if you go up to, if you're crazy, you go to this curve, well, you might not be crazy, you might be having fun. So you just go up the curve, come back, and wander around and drink a full bottle of wine, and you're not very good, and you go back and forth, and so on. And you go back and forth, and your velocity vector is changing. Right? So if it's going forward, it gets some weight, and if it's backwards, it gets a negative that way. So this is area, oriented area. Oriented area. So a multilinear form evaluates oriented area here, added up all over the sphere. And so we have the integral of this two-form alpha over this sphere is the extent. I hope that gives you a little idea what I mean by what are k-forms good for. Okay? That's what are two forms good for. And, now, what I wrote on the board last time was a big long thing. So I'm going to write it again. I guess I'm talking about complex value functions. I don't know, it doesn't matter. Complex value functions. So let's say this big long thing I wrote on the board was that. So far, without saying anything more, this is just a chain of arrows and spaces. But in any case, this is zero forms as functions, that's one forms, two forms, three forms, n forms. It ends a dimension, it ends here because you can't have any more. So if you go to zero. So let's not talk about this too much. We do know that we have a mapping here which is called D. Remember, D goes from functions to one form, and remember what D of F applied to a vector field is just X of the vector field. So D is defined and wonderful. And what we would like to do is extend this notion of D to all levels of this thing. So let's write it here in another color. If we can extend it here and so on all the way. So the question is, can this differential, can the exterior differential, so can the exterior differential, that's the word we use here, I think, differential D, be extended to the full sequence. So from one forms to two forms to three forms, and so on. The answer is yes, but you just don't extend it just for the fun of it. You could extend it to be the zero map or anything you want. You know, if you could extend it, you know. But the desired properties are the obvious ones. Two desired properties. The first property is Leibniz rule, so that means that D of a function times the form. You would like this to be linear. Alexandros really put this, I mean, you were talking about this, you'd like it to be linear, if it would be good, right? But you can't expect this. The best you can expect is exactly this Leibniz rule. So let's just emphasize this as Leibniz. So this is Leibniz rule, this is what you can hope for. And the second thing you hope for is that D squared is 0. So D, circle D, and we write that often as D squared. Should be 0. And that is the theorem that I want to discuss. And I think it deserves the name theorem because somehow it is very fundamental. And the statement is there is a unique extension of the original map, so that the original map, which is from functions to one forms to the full de Rham sequence. De Rham sequence, say call this the de Rham sequence up above, with those two properties, with 1 and 2. Okay? That's a fundamental fact. Let me just re-emphasize what I said last time. In modern mathematics, this rule is called the rule of a connection on a vector bundle. We have vector bundles here, and we have mappings from the vector bundle to higher order bundles. And we want to have such exterior differential forms satisfying Leibniz rule, and this Leibniz rule is the rule of a connection. Those of you who've had some experience with differential geometry will see all connection with Christoffel symbols. Maybe you've seen them: I, J, K, L, M, N, O, P, R, M, alphabetic, gamma, delta. That is nothing more than this. Okay. Now the problem is the second part. If you have some connection, it is almost never the case that if the second order differential operator defined by this connection is trivial. This is a very special case for this situation. This is a God-given situation where you don't have some crazy metric or something called here. You have this situation. And this corresponds to 0 curvature in this bundle. Usually D composed of D squared would somehow or another represent the curvature of the situation, whatever curvature means. Please learn that curvature is not just some funny business like this, or like this, or like this, right? Curvature is an obstruction to solving differential equations. And positive curvature means in the differential equation, you can solve maybe because you have estimates in a positive direction, something like this. This is modern geometry and modern mathematics. It's not just some nice thing where Gauss looks at that and puts it in, Gauss calls that kappa and this stuff. It's not that. Okay? Keep that in mind. Okay. Fine. So, this property, let me call it, let me refer to this as the property that means that we have the Durand complex. I've been careful to call it Durand sequence, but no, it is the Durand complex. And that means that the notion of complex here means this, you have a bunch of maps, God only knows what, but for all these maps you have someplace A, B, C here in the middle. You require at every step here, let's call this, to make it simple, alpha this to beta. The requirement is the beta composed with alpha is 0, and that is the same thing as the image of alpha is contained in the kernel beta. Okay. I'm still reviewing, and I think it still pays off because we're dealing with one of the most fundamental things in mathematics. Did you have a question? Just stretch. It's okay. So let me, if you don't get too bored, let me continue to review for just a few seconds. It's not too boring. So, the naive question is given a K-form alpha, does there exist a K minus 1 form beta? These alphas and betas are not the same. Beta with d beta equals alpha. Okay, that is really a question that occurs, you've seen it in other languages in your physics, and I will convert to that language in a second. But this is one of the fundamental theorems of mathematics. Given a K-form, questions of mathematics, given a K-form alpha, is it d of a K minus 1 form? I hope you understand what a heavy question that is, right? Because alpha is equal, at least in, say, in local coordinates, what was given, alpha or beta? Given a K-form alpha. So alpha is fi1 through fik dxi wedge dx k summed over all possibilities. All possibilities. That's alpha. Right? And now beta is equal to sum j1 less than jk minus 1. G, I get really tired doing this. G k minus 1. dx j1 wedge g x j k minus. Okay. And now the question is, we will define d, but you can imagine d is actually just going to differentiate these coefficients. So d of this beta, when we differentiate these coefficients, we're supposed some incredibly complicated thing going on here. Do we get the right coefficients here? This is an overdetermined system of differential equations. There are many more. See what? So what are you looking for? This is, you know, when you're dealing with children. My granddaughter, you talk to her an equation. You have knowns and unknowns. right? Known and an unknown. Look out for the unknowns because they're flying around in the sky and they're dangerous. So these are the unknowns, right? No, given. These are known, so my granddaughter would know that. These are known, and these are unknown, right? And you differentiate the unknowns to get the knowns, and you have to solve, and that's called a differential equation, right? But you see, it is a necessary condition is that d alpha equals 0. Because if alpha equals d beta, then, what did I want to say? Then d alpha equals d of d beta, which is d squared beta, which is 0. So it's obviously a necessary condition. Okay. So it only makes sense to say, given d alpha with d alpha 0, is it d of beta? Okay. And I said last time
so you want to prove that it's the image of alpha and the kernel of beta, they're equal, that they're included in
so that would be the reasonable question. When is the image of alpha equal to the kernel of beta? Because the kernel, you have to have something in the kernel and beta. So let me read a better formulation. Is given, so I won't formulate it too long, let's repeat with me. I said, given alpha with d alpha equals 0. So this is a necessary condition. Does there exist beta? And so that means is that what you're interested in studying for Q-forms is the quotient of the kernel by the image. So this is a quotient. I emphasize where we are by writing Q here. So we've got to be in the kernel, and we want to know, in some sense I want to know the opposite question. What are those equations that I can't solve? Understanding this object, which we call de Rham cohomology, is understanding the questions, the differential equations which you cannot solve. Systems of differential equations. These are the differential equations which you cannot solve. That is really interesting. Now that's all formal. I haven't discussed exactly what this thing D means. So my goal now is to define D. Okay? This is all very nice. I said you have this definition, it is very great, but I have to define D. So my goal for the remaining goals today the first one is define D with these properties, and then it is unique. And the second goal is to study some examples. And I will study these examples, I will try, I'm not very good at this, in physics language. Physics or engineering language. Now, there are many ways to define this D. It really depends on your viewpoint. It's all the same. I told you it's unique. So it's just a question of how you like to define it. I like to define things in a way that are conceptually interesting. And the way that's conceptually interesting is to first understand the action of the vector fields on the de Rham sequence. So what do I mean by this? Well, I'm going to go someplace in the middle of the de Rham sequence, so talk about Q forms maybe. And I'm going to discuss some things that we've discussed before. The first thing is very easy to understand in my opinion. It's contraction. So I'm going to take a vector field X in the vector field, and I'm going to define in exactly the way you expect a contraction from vector field, from forms of degree Q to forms of degree Q minus 1. And it's interesting in this business, you really should have it at both levels. So I'm going to write it in here. It's going to be defined all along for everything, but I'm going to look at it here. Okay. So far I don't have D. I mean, I drew the picture here as if I had D, but I don't have it yet. So contraction. What is contraction? It's a simplified thing. We've talked about it before. Contraction of a form with a vector field is you simply put the vector field in the first entry of the form, and you get a form of fewer variables. It's clear, right? You just put it, right? You get a form of fewer variables. It couldn't be simpler. So this is the notion of contraction. And I guess the reason we use the word contraction, it contracts the form to one less order. That's the first action on the de Rham sequence, is contraction. So actually, I wanted to go up, but the first thing I'm going to do is go down. Okay, I'm going that way now, instead of this. Now the second thing I'm going to talk about is the Lie derivative. I'm looking again at operations on this de Rham sequence. Operations that are canonically associated as manifold. Well, for this, please recall that if you have a vector field X associated to this vector field, this is fundamental now, recall it please, you have, my notation is now G sub X of T. This is the local one-parameter group. It may not be global. We've talked about this. Associated to X. It may not be global, but it's at least local. Locally defined, and remember that what's the good deal? If you want to differentiate a function, then you differentiate along the action of this group. So what it is, it's let's say differentiate this function at a point x. It's you look at ddt at t equals 0 of f, and then you differentiate along this curve. So the picture you should have in mind is the usual picture. I'm just reminding you of stuff you know. You have a curve of the one-parameter group. Here it is. Here's x, and here's gt of x. It pushes here. Maybe it's only local. It only goes to there. Okay, but it doesn't matter because you're taking a limit as you go to 0 here. So what is this? This is, so in general, this is the x of the field, x of the function without putting x in here. It's ddt of the pullback of the function by the one-parameter group differentiated at time 0. You see, you're pulling back the function by the one parameter group. This is what it means to put the transformation in there and pull it back. Right? So that means another way of looking at this, you see, I recommend that you start to think big time. You should not think in x's, you should think in f's. Here's f, and here's the curve of the function. gt, gt. Okay, it's pullback, but you push the function in a function space with the one parameter group, you're making a curve of functions. And you're differentiating the function along that curve. I mean, what is it to do? It's trivial, right? Okay? You need a linear space, don't you agree? To differentiate, the thing that you're differentiating must move in a linear space. Because you remember what a derivative is. It's something of something plus h. No, I write it for you guys. Something of something plus delta x, right? Minus something divided by delta x. Right, so you see what you do. You subtract it, divide it, and then limit. So you must be in a linear topological space. Otherwise you can do it. Otherwise you can have, you don't need anything else. That's it. So here, we're just pushing around in the space of functions. Here, okay, you're talking about points, but I much prefer this viewpoint here. So that's just a review of how we differentiate functions. Okay. Now I hope my remarks were just halfway clear, because if now we have some linear space where we can do that kind of thing, then we're in business. So I hope you understand that if you're in some linear space, please think big. Well, you're some big associated linear space. Maybe not big, but I was having fun saying the word big. Associated linear space. I don't know, anything big associated with linear space. And you have something you want to differentiate. Let me call it thing, T for thing. Right? So you want to differentiate a thing. Well, you take a curve, you push the thing around, I don't know, I'm going to push it around with time t, and you differentiate it, and that means the velocity vector of this curve at this point thing, whatever the heck thing is. If you can move the thing with the one parameter group, then you can differentiate. That means you take a curve, move the thing around, you get a velocity vector, and this is the derivative of the thing. Right? This is the derivative of the thing. And this will be called the Lie derivative of the thing. Here we call it just the derivative of the thing because it's a vector. This is called the Lie, whatever the thing is. I don't care what the thing is. I only need, as I told you, to be able to write f, you know, I started, and then I move it a little bit, right? It's the thing moved a little bit, minus the thing, right? Divide by a little bit, take limit, right? Now it's interesting, isn't it, right? Well, there's a very interesting point here. Ha ha ha. I said, take it, move it a little bit, take the difference of it here, and divide by the small thing and let the limit go, right? Again, move it a little bit, take that, subtract out here, divide by a little bit, divide by whatever it is, take the limit, right? You see the big problem there? Again, I'll say it again. Take it here, move it over there, just a little, in a little bit of time, take the difference between that, and divide by the little bit of time and take the limit. Okay?
You may not be able to solve it near zero. And
I don't know what you mean.
so the local parameter group, is it always near zero? Okay.
This is okay. There's no tricky difficulty with that. Maybe I didn't explain this. You move it over here. Who said it? Here, you start here, you move it over here, and suddenly I take the difference of it here, this minus that, right? They're different places. Right? They're in absolutely different places. Now, if that's a linear space, you understand what I'm saying? If there's a stupid way to compare these places, I can say, okay, it's here. This is a fundamental geometric concept. You may not be able, in general, to compare these two things. Okay? You may not, in general, be able.
Do you need a box space?
Has nothing to do with functional analysis or delicates of bounding space. It has to do with being able to compare stuff going on here and here. Right? And this now is why the word connection is used, because it is a connection of understanding what is going on here and here. And here, we in fact do have a way of doing this, because we're dealing with linear spaces of a trivial nature. We suppress this difficulty. Okay, we suppress the difficulty. I think people here, a number of you in physics, can understand this very well. It's very difficult to compare something going on here and here, right? You need a connection, a way of connecting these two spaces. That's why the word is called connection. And that implicitly in this discussion, there is some background connection. Let me just say that and leave it as. Okay, so this thing is not so abstract. In our case, what we have is here a differential form. So a differential form is a Q form. It's just in this space. For those of you who are amused by functional analysis, this space is of course not a bounding space, it's a Frechet space, but it's a reasonable linear topological space. There's no difficulty with that kind of stuff. And what you do, you move it, so you take this thing, and moving it is just pulling it back. Now I haven't discussed this at the level of K forms, but it's the same as at 1 forms. You pull it back, and you differentiate it. Differentiate the result. And this is the lead derivative of this form. Okay. You're pushing it around with a vector field. You're pushing it around with the integral curve of a vector field, the action of a vector field, and differentiating along that. Now, let's look what we have so far. We have EQ, and we're going backwards with this stuff, contraction from EQ plus 1 going backwards, going even backwards here, EQ minus 1. And now Lie derivative differentiates here. So you have two operations on the Durand sequence. First of all, contraction going back, and then differentiating, and you stay in one. You don't change the degree of the form. I mean, it's completely clear. These are all K forms, and you take the limit, you get a K form or Q form or whatever it is. So you don't move back and forth. It stays in the middle. Now comes some step of mathematical sophistication, a little bit. Situation like this, we're looking for adjoint operators. D. So in some sense you should think we should try to find something that's the opposite of contraction. Yeah? You should find it, you can't do this of course, but exactly opposite, but it's an adjoint operator. And we now define D, it's somehow very much related to this differential operator. You might find this definition very surprising, but it is a beautiful definition, and I feel the correct definition is this. You might argue about the sign here. Some people might want to take a commutator, but if you actually, this is bosonic. And so you should really somehow see that this is the right way to think. Look what I'm saying. I'm saying I'm looking for an operator. If you go down and up here, you land in here. And you go up and down and you land here. I'm saying, you see, this is saying, this one is saying you go up and back down. And here you're going down and back up. Okay? And so you add these two things, and you want to get your original operator. Now this is a definition.
But Professor, what are we defining? We're defining
D
here.
I've defined it.
Not L.
Yeah, this is subtle, but I've defined it. So first please write this formula down. This formula defines D by recursion. You see? By induction or recursion. Right?
But Professor, could you make sure that it works for all the cube, because we only work in one cube here. What about
Any cube. Okay, let's be very slow. Okay. I had to, if you wish, it was what Mihai suggested last time. I had D1, D2, D3. Okay, but we suppressed that notation. Okay. So as you say, you want it for all. Okay. Here's the slow definition. Maybe D0 goes from functions to one points. Okay, I've already defined it. Okay. Now I want to define this recursively through Q. Right. Let us suppose I've defined it up to, I don't know, Q minus 1. Okay. That means that this thing is defined. Right? This went down from Q to Q minus 1. That means this thing is defined. You get it?
Yeah. Okay, I see.
So it means, but this is not yet defined because it goes up and down. So to satisfy you, and I'm very happy with your I'm saying that the definition of the left, I'm going to put everything over on the other side, is lead derivative minus this. This is defined anyway. This is defined anyway. This is defined by recursion, by our induction hypothesis, or whatever you call it, recursion hypothesis. Now, that means the left-hand side is defined for every x. Okay? Now, it's pretty easy to believe, and you can check it easily. If this thing is defined for every x, then it's defined. I mean, you just have to check. I mean, it's defined for every x, correct? Okay, that's the definition. Now, the advantage with the definition is very conceptual. You see really what it is, conceptually what it is. And there are several advantages. The first advantage with this, it's canonical. I introduced nothing. Nothing was introduced here. I used the circle for maybe God or whoever it is, the prophet, whoever it is. The circle gave us this, right? I didn't introduce anything. Okay. This is canonical. Okay. The second fundamental thing, if you look at this definition, is that D is a local operator. So, by definition, D, and I'm going to write this in quotes, is local. This means, in order to compute D, you only need to know, D is defined on a differential form. D is defined here. So, in order to compute D on a form, you only need to know that form locally. Because look what's the part of the definition. Well, recursively, we only need to know that locally. That's obviously, you only need to know the form locally to do it here. You only need to know the form locally here. I mean, it's just derivative locally. Therefore, you only need to know the form locally here. It's a local operator. This is fundamental. Okay, that means I can compute it in coordinates, right? That means I can just say, if I want to understand this thing, I compute it in coordinates. Okay? Fine. Now I will give a little elementary homework assignment with big hints to prove that following is very easy. In coordinates. A 3-step homework exercise that you easily will solve, but we'll have fun solving. It is facts that you will just apply the definition. D of dxi, so this is a multi-index notation, is 0. Believe me, you can use this definition to prove that d of dxi is 0. Then after you've proved this, since that's the case, you can prove that d of f times xi is equal to df times dxi. That's also an immediate consequence. And then after that, you immediately prove d of f times any omega is equal to df, so I like to write it f d omega plus df omega. That's very close to the same thing here. See, the fact is we can work in coordinates, and it's very easy to prove things then. And finally, this is the Leibniz rule, and finally it's very easy to check in coordinates. Check the d coordinates. Okay. Now, if you look at this, you will enjoy this homework exercise. If somebody comes walking in from the street, he will say, usually the definition of D is this. This is the usual definition. Right? Because every form is just function times the dx, right? Yeah? But I dare you, I challenge you to prove that that definition is independent of the coordinates. And I challenge you after that to prove this formula. Yes? The main thing is this formula. The main thing is this definition here. To know what the right property of this differential operator is, that it is in this sense an adjoint operator for contraction. Okay. This formula many people call the magic formula of Cartan. And I emphasize which Cartan. There are two great Cartans, father and son at least. This is A.D. Cartan. The father. So, again, I now have defined D this way, and by elementary checking, which will be a fun homework problem, you have proved everything you need. Okay? And it's uniquely defined. I mean, this proof is uniquely defined. It has to be defined this way. There's no choice. What did I promise? That was the definition of D. Has these properties. The only thing to keep in mind is the magic formula of Cartan. Well, of course, in this property here. Now, let's deal with two examples, and then you can have a nice weekend without me. Okay? Example 1. let's consider n to be R2 minus the point. Okay? R2 minus. Now, here, we have a basis, a frame, for the cotangent bundle of n. And I'm not stupid. I'm going to use a frame that everybody likes to use, namely polar coordinates frame. Right? Right. So is d theta dr. Keep in mind that r is a well-defined function, so that is really d of r. Keep in mind that theta is not a well-defined function. That this notation is stupid. Theta is not well-defined, right? Right? It started at 0. What do you mean? How do you know? I give you a vector, you tell me theta. You're right? You tell me 60 degrees, and I tell you, what is it? 360 plus 60. What is that? It's, I don't know, 420. Right? We have a big debate about whether it's 420 or 60. It doesn't matter. It's not well-defined. Okay? However, d theta is a well-defined thing. Okay. Now I'm interested in the de Rham cohomology of n. So I'm interested in kernel of in this case it's H1, so I'm going up D1 from 1 forms to 2 forms. Divided by image of 0 forms, okay, D0 functions, everybody knows what this is, to 1 form. Okay. And I notice that the form, this is not d of theta, but I notice that this is easily seen to be in the kernel of D1. You can easily check that this, well, this is in the kernel of D1. It's locally d of theta, and that's enough. You understand? Locally it's defined. You get it? I can define theta here at near 60 degrees as being 60 and then a little bit more. It's the problem globally defining that, right? So if it's locally well defined, then it's d of theta. And I just told you d of theta is 0. And I just told you that d is a local operator. So it doesn't care what goes on globally. Okay? So d in this thing is 0. And so I'm interested in the cohomology class of d theta. I mean, it's a terrible thing. This is just a horrible thing. Let's call this thing alpha because, I mean, it's not d of anything. Yeah? This is really bad thing from elementary mathematics. You call that d theta, but it's not, theta is not well defined, so you should never call it d theta. Right? Let's call this alpha. So alpha is here, it's a closed form, and I want to see what happens in cohomology. So I want to compute it. Let's compute d theta. Have you ever computed d theta? I don't know. I don't know whether it helps to compute it or not, but I do some computing always. I get up at 5 in the morning, begin drinking coffee, and compute for a long time, answer emails, look at American politics, get joyous that Obama won, and then I compute some more, and probably a lot of it is nonsense, but then at least I had some fun, and then I have some muesli, and then I try to be more serious. Okay. X equals r cosine theta. Right? I'm now back in the, I'm thinking when I was a child, and they taught me, you know, in kindergarten you learn this stuff. And then you say Vx is, well, it's Leibniz rule, that's so I know what to do. It's cosine theta dr minus sine minus r sine theta d theta. And dy y is equal to r sine theta. And dy is equal to sine theta dr. Sine theta dr. Now I have to differentiate with respect to theta. That's a plus sign. R cosine theta d theta. Okay. Right? And now I multiply the top by sine theta and the bottom by cosine theta and subtract, if you don't mind. No, subtract the top from the bottom because I don't like this minus sign. Okay? But I want to get this in terms of x, so I multiply the top by r cosine. You see, I knew you wanted to check if I could do any of this stuff. This is x times x. This is, well, I already made a mistake, you see. I wanted to multiply this by sine theta. Right? And so this is what? Right? And then this is sine theta times r cosine. I don't know. It doesn't matter what it is because I'm going to cancel it. And then this is minus, okay, I multiply that. This is r squared sine squared theta d theta. And then what I will multiply this by r cosine theta times dy. This is x. And I'm going to get some junk. This cancels. And then I'm going to get here plus r squared cosine theta. You see, you can do this when you wake up in the morning or even when you've drunk too much at night. So when you, what am I going to do? I'm going to subtract the top from the bottom and kill this, right? Whatever it is. And what I'm going to get, I'm going to subtract from the bottom, and so what I get is x dy, that's the bottom, minus y dx is that plus that, so that's r squared d theta. And so I'm going to divide by r squared, and that's x squared plus y squared. And that is the change of coordinates, the change of frames from d theta dr to the rectangular coordinates dx dy. And you notice, without thinking, I picked up a pole at the origin. Right? I picked up a pole at the origin. Okay. Well, now, that is in rectangular coordinates. You might be interested, why on earth this thing, oh, this should be alpha. And now if you suppose, that's very interesting, I picked up a pole, right? I picked up a pole at the origin. And you see, I get a residue at that pole, right? If I integrate this thing, right? Let's try to integrate alpha over the circle. Over the circle, S1. Well, if you check what you integrate here over the circle, it's d theta over the circle. I mean, if you believe in anything, the circle, where maybe you have God or whoever it is, you know what the answer to this thing is, right? It's 2 pi, right? You know. And now suppose that alpha is equal to df. Well, if alpha is equal to df, everybody in this class knows the fundamental theorem of calculus. If you integrate df from things to things, it's f at one end minus f at the other, right? Right? That's the fundamental theorem of calculus. Well, if you integrate df over a closed curve, you get 0. Right? So this is not df. Its integral is 2 pi, and the reason this integral is 2 pi is you picked up, without understanding anything, you found a differential form in this cohomology which reflects the fact that there's a non-trivial topology caused by 0. Understand? You found this pole and you found, without trying, the reason this cohomology is non-zero. So this is analysis, not being able to solve a differential equation, Okay? Because of non-trivial topology. You see, this is one of the most beautiful starting places in all of mathematics. It's a starting place. Well, I have maybe, well, I think that's a nice place to stop. I'll give some more examples next time about a physical nature. With curl, you've heard the word curl in physics, and gradient and all these usual things you have. This is hidden here, that's physics notation for this, and I will explain in dimension 3. Okay, I will explain that next time. I think it's nice if you know what these words mean. Right? You've heard these words, right? Yes, I always have to look them up because I don't know what they mean. Okay, thanks. Have a nice weekend.